Good morning and welcome back to the subject open channel flow, hydraulics and hydraulic machinery. We are in unit 1. Yesterday we discussed about various types of open channels and classification of flows in open channels like steady and unsteady flow, uniform, non-uniform flow, laminar, turbulent flows, subcritical, critical and supercritical flows, etc. We discussed. Apart from that, we have seen about the geometrical properties of various sections like rectangular section, rectangular channel section, trapezoidal channel section, triangular channel section, and then particularly these three. As far as UG syllabus is concerned, I suppose these three would be more than enough. And we have reduced the expressions for hydraulic radius, then hydraulic depth for these different types of channels. Today's class, we look at the velocity distribution and the correction factors like kinetic energy correction factor and momentum correction factor. So what is this velocity distribution? In our fluid mechanics subject, we already studied about the velocity distribution for the pipe flows. So if you take a pipe flow, how the velocity distribution would be? If we take a laminar flow, if we take a turbulent flow, once again, the velocity distribution would be different. However, for a typical pipe flow at a given section, the velocity distribution may be like minimum velocity at the pipe boundaries and the maximum velocity at the farthest point from the pipe boundary, which is equal to the center line of the pipe. So this is the maximum velocity, and these two are the minimum velocity points. So this is how there may be velocity distribution at a given section for a pipe flow. Similarly, for the open channel flow also, we have the velocity distribution at a given section. Let it be a rectangular channel section, or a trapezoidal channel section, or a triangular section, or a circular section. You may have the velocity distribution. Here also you may notice that the pattern of the velocity distribution in all the cases is almost similar. You may see here, it is almost similar for all four types of open channel sections: rectangular, trapezoidal, triangular, or circular. Only thing is, as compared to the pipe flows, this velocity distribution is different. This is point number 1. As compared to the pipe flows, this velocity distribution is different. In the case of pipe flow, you must have seen at a given section, the maximum velocity is occurring at the center. But whereas here, in all these open channel sections, the maximum velocity is not at the center. It is not at the center for all these sections. Also, it is not at the top. That means it is not at the free surface also. Slightly below the free surface, the velocity is maximum. Slightly below the free surface, the velocity is maximum for trapezoidal. Similarly for triangular. Similarly for circular. So, this is how there is a change, a difference in the velocity distribution for the open channel flows as well as for the pipe flows. Okay. So, at a given section, if the distribution of the velocity is presented in a graphical form, we may get a shape like this, having non-maximum velocity at the pipe, at the channel boundary or at the free surface, but maximum velocity will be slightly below the free surface. Slightly below the free surface. Similarly, the velocity at the channel boundary is not 0. You may notice here the velocity at the channel boundary is not 0. Let us have a discussion about this velocity distribution. The pressure of corners and boundaries in an open channel causes the velocity vectors of the flow to have components not only in the longitudinal direction but also in the lateral direction as well as in the normal direction to the flow. You may be having the corners and the boundaries which are causing the velocity variation in all the directions in the open channel flow. Longitudinal direction, lateral direction, also in the normal direction, there is the variation in the velocity components. However, the maximum variation for the velocity component will be there only in the longitudinal direction. Only in the longitudinal direction. That means along the length of the channel, along the length of the flow, there would be variation as compared to the variation in the remaining two directions like normal and lateral directions. So, we consider that the flow is varying only in one direction. So, the velocity V is designated for the longitudinal component, ignoring the variation in the velocity in the remaining two directions. So typical the velocity distribution for a open channel may be like this. So at the channel bed, the velocity is not 0. It is some minor velocity will be there. As the depth from the channel bed is increasing, the velocity also would be increasing. Towards the free surface, there will be some velocity which is less than the maximum velocity. There will be some velocity which is less than the maximum velocity. So this is how the typical velocity distribution in an open channel flow. The velocity flow at any channel section is not uniformly distributed. Unless the fluid is ideal, it cannot be uniformly distributed. We have seen water flowing in a pipe flow also in the previous slide. Water flowing in a pipe or any other liquid flowing in a pipe also we have seen the velocity distribution variation is there from the center to the boundaries. Unless the fluid is ideal. If the fluid is ideal, what will happen? Since there is no resistance, everywhere at a given section, the velocity will be constant. The velocity will be constant. But since water is also a real fluid possessing the viscosity and there is some resistance to the motion from the channel boundaries as well as from different layers of the water, you may identify that there is variation in the velocity. There is variation in the velocity which is not uniformly distributed. The non-uniform distribution of velocity in an open channel is due to the presence of free surface and the resistance, the frictional resistance along the boundary of the channel. So there is a free surface. Free surface also offers the resistance. That is the reason why the maximum velocity is not at the free surface. Because over and above the free surface, the overlying fluid is atmosphere, and that atmosphere also offers resistance for the motion at the free surface of the channel. This results in non-maximum velocity at the free surface. So the velocity is not maximum at the channel bed. The velocity is not maximum at the free surface. Maximum velocity will be somewhere in between these two. Velocity is non-zero at the boundary, gradually increases with the distance from the boundary. Maximum velocity occurs below the free surface because at the free surface there will be secondary currents, resistance to the motion of the fluid. So you have seen the velocity distribution like this. Typical rectangular section if you take at the boundary, at the channel bed, it is a non-zero velocity. At the free surface, it is a non-maximum velocity. The maximum velocity occurs slightly below the free surface. This is true for any of the shaped channel sections. Let it be rectangular, let it be trapezoidal, let it be triangular, let it be circular section. For all these cases, you can notice that the maximum velocity does not occur at the free surface, but it occurs below the free surface because over and above the free surface, there is overlying fluid atmosphere offering resistance, and there will be secondary currents which may be there. The velocity distribution in a channel is measured either with the help of a pitot tube or a current meter. You have studied about the pitot tube in your fluid mechanics subject. Pitot tube, pitot static tube, etc. for measuring the velocity. Similarly, for open channels, the device used is also current meter or even pitot tube also can be used. Morning yesterday's class we have seen about piezometer for measurement of pressure. Similarly, for measurement of velocity, the device used is pitot tube or current meter in the open channels. In a straight reach of a channel, maximum velocity occurs below the free surface at a distance of 0.05 to 0.25 meters of depth of flow. If y is the depth of flow, the maximum velocity occurs about 0.05 y to 0.25 y. Y is the depth of flow. So from the free surface, about 0.05 to 0.25 depth, the velocity becomes maximum. The velocity distribution in a channel section depends on three parameters. Shape of the channel section, we have seen for different shapes like rectangular, triangular, trapezoidal, circular, you have different shape, different velocity distribution. So it depends on the shape of the channel section, roughness offered by the channel boundaries, and presence of bends in the alignment of the canal. Suppose you have a channel straight or you have a channel with a lot of bends. So if the alignment is having more and more bends, it will have the impact on the velocity distribution at a section. So there are three parameters which will be affecting the velocity distribution in an open channel. Shape of the channel, roughness of the channel, presence of bends in the alignment. The mean velocity of a flow, this is usual practice. Even in fluid mechanics, for pipe flows also, wherever there is non-uniform velocity distribution, we go for average velocity, mean velocity. We must have taken up that in our fluid mechanics subject. Same thing here also. So the mean velocity or average velocity of flow of a channel in a channel section can be computed from the vertical velocity distribution curve obtained by the actual measurements. If you take the actual measurements and take the average of all that, then you will be getting the mean velocity. How do you get the measurement of actual measurement of the velocity? With the help of a device known as Petard tube. So with the help of the Petard tube, Petard tube is a simple glass tube bent at right angles. Simple glass tube bent at right angles. So one end of this Petard tube is open to the atmosphere, and the other end of the tube is connected, or other end of the tube is placed at a point where the velocity is required to be measured. If the flow of velocity is taking place in an open channel in one direction, facing that flow direction, you have to keep this tube. So corresponding to the velocity here, there will be increase in the water level in the Petard tube, and you will be able to get the measurement h. So root 2 gh, of course, multiplied with certain coefficient will give you the velocity v. The velocity v. So the mean velocity of flow in a channel section can be computed from the vertical velocity distribution curve obtained by the actual measurements. It is also observed that the velocity at a depth of 0.6 y, 0.6 y, that means 0.6 times the depth of flow which is measured from the free surface, is very close to the mean velocity of a flow. Or you may take the average also, like the velocity at 0.2 y, velocity at 0.8 y, and take the average of these two, maybe providing you the average velocity or mean velocity. Average velocity or mean velocity will be the velocity at a 0.2 y plus velocity at 0.8 y divided by 2. Average of these two will be equal to the average velocity. On account of non-uniform velocity distribution over the channel section, we have to provide certain correction factors for computing the kinetic energy as well as the momentum, because we are calculating all the kinetic energy or we are calculating all the momentum based on the mean velocity capital V. Mean velocity or average velocity capital V. But when you compute the same kinetic energy by considering the actual velocity distribution, both the kinetic energies will not be equal. Both the kinetic energies will not be equal. Similarly, for the momentum also, both the momentum fluxes will not be equal. I repeat again, kinetic energy calculated based on the actual velocity distribution is different from the kinetic energy calculated based on the mean velocity. Mean velocity is only a computational value. Just like you are taking the average velocity, like v.2 plus v at 0.8 divided by 2 gives you the average velocity. So if you compute the kinetic energy based on this average velocity, this is not equal to the kinetic energy calculated based on the actual velocity distribution. Similarly, the momentum flux, which is calculated based on the actual velocity distribution, is different from the momentum flux calculated based on average velocity. So to account for this, to account for the variation in these kinetic energy and momentum, we introduce the multiplication factors. These factors are kinetic energy correction factor alpha for computing the kinetic energy and momentum correction factor beta for accounting for the momentum. So kinetic energy correction factor alpha, momentum correction factor beta. So these two will be applied while arriving at the actual kinetic energy, while arriving at the actual momentum. Because if you are calculating based on the average velocity, you will be getting some value of the kinetic energy. This should be multiplied with alpha, so that you will be getting the corrected kinetic energy. Corrected kinetic energy. Similarly, if you are computing the momentum based on the average velocity, that should be corrected by multiplying with a factor known as momentum correction factor beta, so that you will be getting the corrected momentum. These two are the multiplicative factors. Alpha and beta are the multiplicative factors. That means whatever kinetic energy that you are getting based on your average velocity, multiply alpha. Multiply alpha, you will get the corrected kinetic energy. Similarly, multiply with beta, the momentum, you will get corrected momentum. So value of alpha may be varying from about 1.03 to 1.30, and beta varies from about 1.01 to 1.10. So one-dimensional method of flow analysis is adopted. What is this one-dimensional method? While we are considering the variation of the velocity in the three directions, like normal direction, longitudinal direction, lateral direction, it becomes a three-dimensional analysis. If you are considering the variation in the velocity in all the three directions, lateral, longitudinal, and normal, then it becomes a three-dimensional method of flow analysis. But for the sake of our mathematical convenience, we assume that the variation is more and maximum only in the longitudinal direction, and in the remaining two directions, the variation may be very less and hence may be neglected, and that means, and hence may be assumed to be constant. This is one assumption that we are making. We are adopting only one-dimensional method of flow analysis. We are adopting only one-dimensional method of flow analysis instead of taking three-dimensional method of analysis. This assumption is justifiable because when you have three components, velocity components in the lateral, normal, and longitudinal, the maximum variation in the velocity is coming up only in the longitudinal direction as compared to the remaining two directions, normal and lateral direction. They are almost constant. Variation is less, and hence the assumption is justifiable even if you consider one-dimensional method of flow analysis. Flow properties such as velocity, pressure gradient in a general open channel flow situation can be expressed to have the components in the longitudinal as well as in the normal directions. The analysis of such a three-dimensional problem is very, very complex. However, for the purpose of obtaining the engineering solutions, a majority of open channel flow problems are analyzed by one-dimensional analysis, where the mean or representative properties of the cross-section are considered and their variation in the longitudinal direction are analyzed. So you are taking only one direction, longitudinal direction, trying to analyze along the longitudinal direction what are the changes that are coming up for the velocity by making an assumption that the variation in the other two directions of the velocity components is neglected. This method, when properly used, not only simplifies the problem but also gives meaningful results, because we are making a justifiable assumption. The results are meaningful, the results are directly applicable to the practical situations. In open channel flows, velocity is not uniform over the cross section. So the kinetic energy expressed also is not correct, because you are calculating the kinetic energy something like half of mass into velocity square, half m square, say kinetic energy, half m square. What is mass there? M. What is V? Velocity. What is this velocity? It is obviously the mean velocity. It is obviously the mean velocity. So, but strictly speaking, you need to take the actual velocity distribution. Instead of considering the actual velocity distribution, we are confining ourselves to take mean velocity. And hence, we are applying a correction. So, kinetic energy calculated based on the mean velocity V is not equal to the kinetic energy calculated based on the actual velocity small v. Actual velocity is varying. It is a local velocity which varies from channel bed to the free surface, having the maximum value slightly below the free surface. This is what we have seen in the figure just now. So a mean velocity capital V for the entire cross-section is defined on the basis of longitudinal component of the velocity small v. If small v is the longitudinal velocity at a particular section at a particular point, then the mean velocity V can be related by this equation. How do you get this equation? How do you get this equation? Small v is the velocity at any given point of a given section. At any given point, this small v, the velocity will be varying depending on the velocity distribution. Depending on the velocity distribution, just I'll show. So depending on the velocity distribution, the value of the small v may be varying. This is the maximum value small v. So here it is less than that. Here it is less. Like this, it will be moving. So there is a variation. There is a variation in the velocity, and small v is representing the local velocity at different points of a given section. Then if dA is the corresponding elemental area, then what do you get? Area multiplied by velocity gives you the discharge. Since you are taking a small element of having the area dA, you will be getting the discharge through that elementary strip only. V into dA is the discharge through that elementary strip. If you want the total discharge, integrate. If you want the total discharge, integrate with respect to the entire cross-sectional area or with respect to the entire wetted area, capital A, then you will be getting integral of V into dA gives you the total discharge. This is based on the actual velocity distribution. But based on mean velocity, if you see, A is the wetted area for the entire cross-section and B is the mean velocity. Area into velocity gives you what? Area into velocity gives you discharge. So the discharge calculated based on the mean velocity is A into V. The discharge calculated based on the local velocity is integral of V into dA. Both are the discharges. Equating both, the velocity V will be equal to 1 by A integral small v into dA. This is how the mean velocity V at a given section is related to the local velocity small v, the local velocity small v. So the velocity V is used as a representative velocity at any given cross section, and the discharge of course would be equal to V into A, the actual discharge based on the mean velocity, integral small v into dA based on the actual velocity distribution. The kinetic energy correction factor alpha is given to be alpha is equal to 1 by A integral of small v by capital V whole cube into dA. What is capital V? The mean velocity taken as a representative velocity at a given section. Small v is the variation in the velocity, like a local velocity which may be varying at a different points at a given section. Of course, capital A is the wetted area and dA is the elementary strip area, elemental area that you have considered. So the kinetic energy correction factor alpha is given to be 1 by A integral of small v by capital V whole cube into dA. Similarly, the momentum correction factor beta is given to be 1 by A integral of small v by capital V whole square into dA. What is the difference? In this case, small v by capital V to the power 3 for momentum correction, for kinetic energy correction factor. Here, small v by capital V whole to the power 2 for the momentum correction factor. So this is how alpha and beta can be evaluated. Alpha is equal to 1 by A integral small v by capital V whole cube dA, and beta is equal to 1 by A integral small v by capital V whole square into dA. You can derive the expression for both also. To derive the expression for the kinetic energy correction factor alpha. To derive the expression for kinetic energy correction factor alpha. So to derive that, maybe any arbitrary shaped channel you may consider. For this arbitrary shaped channel, consider a small elementary strip. This hashed line is the elementary strip of the channel section having area dA, having the elemental area dA at which the local velocity is small v. So small v into dA gives you what? Area multiplied by velocity gives you the discharge. So the discharge or volume rate of flow would be equal to V into dA, or the discharge capital Q will be equal to area into velocity A into V, which is equal to integral of V into dA. The mass rate of flow or mass per unit time is equal to mass density rho into volume rate of flow. How do you get this? The mass rate of flow, mass density into volume rate. Volume rate is discharge. Volume rate is discharge, and mass density is rho. So rho multiplied by V volume rate, the discharge is equal to V dA. So rho into V into dA gives you the mass rate of flow. In other words, to say mass density by definition is mass by volume, mass per unit volume. So mass by volume into volume rate, volume by time, volume by time, mass by volume into volume by time. So volume both in denominator and numerator gets cancelled, and you have mass per unit time. Mass per unit time is called mass rate. Mass per unit time is called mass rate of flow. So to get the mass rate of flow, mass density multiplied by volume rate of flow, rho multiplied by V into dA. Then the corresponding kinetic energy flux can be calculated. Kinetic energy flux or kinetic energy per unit time is called kinetic energy flux. So kinetic energy per unit time would be equal to, how do you compute kinetic energy? Half of m square. As we all know, KE, kinetic energy half m square, half of m is mass into V square. V is the velocity. Half of m square per unit time, same thing, per unit time. Half of mass V square per unit time. You just keep this V square here, mass per unit time. Half into V square into mass per unit time, or V square by 2 into mass per unit time. Mass per unit time is mass rate of flow. Just now we have seen mass rate of flow, mass per unit time, which is equal to rho V into dA. Substitute that. Rho V into dA into V square by 2. Rho V into dA into V square by 2. This is the kinetic energy flux through the elemental area dA. If you want the total kinetic energy for the entire cross section, integrate it. So for total area, the kinetic energy flux based on the actual distribution, velocity distribution would be integral of rho v dA into v square by 2. Let this be equation number 1. Equation number 1 is kinetic energy flux based on actual velocity distribution. Similarly, you calculate the kinetic energy flux based on mean velocity distribution and equate both. So based on the average or the mean velocity distribution, how do you compute this kinetic energy flux? So the total kinetic energy flux per unit time would be equal to half of m square, once again, half of m square per unit time. Half of m is mass. And since you are taking the average velocity, this becomes capital V. And what is mass per unit time? Mass per unit time is mass rate. Mass per unit time is mass rate. So mass density into volume rate. Mass density rho into volume rate is discharge, area into velocity. Area into velocity for mean velocity, capital V, it becomes A into V. So rho into A into V or rho A V square. Rho A V square is the mass rate of a flow. And since you are taking this kinetic energy flux based on the mean velocity distribution, you need to correct it by multiplying with the correction factor alpha. So alpha into half of m square per unit time will be the kinetic energy flux based on the mean velocity distribution. So alpha, half of alpha into mass per unit time into v square. Mass per unit time into v square. Half of alpha into mass per unit time is mass rate, which will be equal to mass density into volume rate into v square. Or half alpha into mass rate. The mass rate is rho AV into v square. So half of alpha into rho AV cube is the kinetic energy flux based on the average velocity distribution. Equation 2. Equation 1, kinetic energy flux. Equation 2, kinetic energy flux. One is based on actual velocity and the other is based on the mean velocity and corrected it by multiplying with alpha. So from equation 1 and 2, equating both, you will be getting alpha will be equal to integral small v cube dA divided by into v cube into dA. Half of gets cancelled here, and hence alpha will be equal to 1 by a small v integral of small v by capital V whole cube into dA. This is the expression for the kinetic energy correction factor alpha. Same thing is valid even in our pi flows also. In our pi flow, when you are applying the Bernoulli's equation, you will be taking the total head at section 1 must be equal to the total head at section 2. How do you compute the total head? It is the sum of the three heads, P by gamma plus Z plus V square by 2G. But if you take the real fluid, you should take alpha V square by 2G. Alpha is the kinetic energy correction factor. And this kinetic energy correction factor will be computed using the same formula, 1 by A integral small v by capital V whole cube into dA. Okay, so this must have been derived there at your fluid mechanics level also. But I'm taking this independent as if no, you have not heard of KE correction factor alpha or momentum correction factor beta. As if you have not heard, I'm deriving the equations. Those who have already derived this alpha and beta earlier, you must have appreciated and noticed that the same procedure has been followed here also. But in the case of only thing is, in the case of pipe flow, you must have taken elementary strip, elementary ring there because it's a pipe flow cylindrical. But in the case of open channel flow, you have taken a small strip of elementary area. That is only the difference. But the final expression is same. Alpha is equal to 1 by A, small integral of small v by capital V whole cube into dA. Similarly, to derive an expression for the momentum correction factor for elementary area dA and the volume rate will be equal to VdA, mass rate will be rho VdA, same thing. So the momentum flux will be mass by time into velocity. Mass by time is called mass rate, rho VdA into small v. So the total momentum flux will be integral of rho v square dA, integral of rho v square dA. This is equation 1. Based on the average velocity, if we take, if V is the average velocity, area into velocity is the discharge, rho into area into velocity gives you the mass rate multiplied by the average velocity V, rho A V square. This is to be corrected by multiplying with the multiplication factor beta, momentum correction factor. So correspondingly, the corrected momentum flux will be beta into rho V square, equation 2. So from equations 1 and 2 and equating both, you will be getting integral of rho V square dA is equal to beta into rho V square A. Hence, beta will be equal to 1 by A integral small v by capital V whole square into dA. We have now used the expressions for the kinetic energy correction factor alpha, momentum correction factor beta. At this point, I would like to impress upon one very important point. Why should we compute this alpha and beta? I would like to retrace again. Why should we compute this alpha and beta? Correction for kinetic energy, correction for momentum, because we are calculating the values of the kinetic energy, value of the momentum based on the average velocity distribution. Strictly speaking, you should consider only with the actual velocity distribution. Since you are taking only, you are using mean velocity, you are trying to correct it. You are trying to correct it by multiplying with the appropriate correction factor, either alpha or beta for kinetic energy or for momentum respectively. Work out one or two problems related to this. The energy and momentum correction factors alpha and beta for open channels are given by this. For a given open channel, the value of alpha and beta are given. Alpha is equal to 1 plus 3e square minus 2e cube. Beta is equal to 1 plus e square, where E is Vmax by V minus 1. Capital V is the average velocity, Vmax is the maximum velocity. So I'll imply, small v is the local velocity. Determine alpha and beta if the velocity distribution is given by, the velocity distribution for this is given by V by Vmax is equal to y by y0 to the power 1 by 7, where y0 is the total depth of flow. Depth of flow in the channel is y0. Depth at any point is taken to be y in this case, in this problem. Okay, so V by Vmax is equal to y by y0 to the power 1 by 7. So for this velocity distribution, given the values of alpha, given the expressions for alpha and beta, you need to compute the values of alpha and beta for the velocity distribution given. So we have a very standard expression, the discharge Q equal to area into velocity continuity equation, or the discharge equation which you must have taken. Discharge Q is equal to area into velocity. Area, capital A, velocity V, the mean velocity. The mean velocity. If you would like to take the actual velocity or the local velocity through elementary strip, then V into dA is the discharge through that elementary strip, and integrate the total thing, you will get the total discharge. So equating both the things, the discharge Q based on average velocity, the discharge Q based on local velocity. Small v into dA based on the velocity distribution. Then Q is equal to area into velocity AV is equal to integral of V dA. What is small v? Small v is the velocity which is given in this problem with the relation V by Vmax is equal to y by y0 to the power 1 by 7. This is the relation given. Or else small v is equal to Vmax into y by y0 whole to the power 1 by 7. So substitute that value. Substitute for small v. Small v is equal to Vmax into y by y0 to the power 1 by 7 into dA. What is this dA? Area of the strip. So when you are taking a small elementary strip of thickness dy, the unit will 1 into dy is the elementary area. Elementary area. Then take out all the constants from the integral. Vmax by y0 to the power 1 by 7 can be taken out. Then you have integral of y to the power 1 by 7 dy. Integral of y to the power 1 by 7 dy. That means y to the power 1 by 7 plus 1 divided by 1 by 7 plus 1 between the limits of 0 to y0. X to the power n plus 1 by n plus 1. So you need to between the limits of 0 to y0. So you need to implement the upper limit as well as the lower limit of integration. You will be getting y0 to the power 1 by 7 is here, and you have 1 by 7 plus 1. That means 1 plus 7 by 7. 1 plus 7 is 8 by 7 in the denominator is there. So it becomes 7 by 8. 7 by 8 into Vmax into y0 to the power 8 by 7 into y0 to the power minus 1 by 7. How do you get y0 to the power minus 1 by 7 here? And you're applying this 1 by 7 plus 1 here and y0 to the power 1 by 7 here. So you'll be getting this 1 by 7 is in the denominator. So if you take to the numerator, it becomes y0 to the power minus 1 by 7. Minus 1 by 7. Here it is 1 by 7 plus 1 or 1 plus 7 by 7, 8 by 7. So y0 to the power 8 by 7, y0 to the power minus 1 by 7. So it is 8 by 7 minus 1 by 7. 8 by 7 minus 1 by 7. 7 by 7, 1. It becomes simply y0. So accordingly, the discharge Q will be equal to 1 into y0 into V would be equal to 7 by 8 Vmax into y0. Or V will be equal to 7 by 8 Vmax, and with the simplification, you will be getting 7 by 8 Vmax, y0 to the power 1 by 7, y0 to the power minus 1 by 7. Or V will be equal to 7 by 8 into Vmax, which gives you the relation between the mean velocity as well as the max velocity. Mean velocity capital V is equal to 7 by 8 into maximum velocity Vmax. And it is given that small e is equal to Vmax by V minus 1. Vmax by V minus 1. Vmax by V minus 1. Substitute that. Vmax by V. The average velocity is 7 by 8 into Vmax minus 1. So you are getting the value of E to be equal to 1 by 7. Alpha will be equal to 1 plus 3e square minus 2e cube. This is what is given in the problem. So alpha is equal to 1 plus 3e square minus 2e cube. E is 1 by 7. Substitute 1 by 7 here. You are getting alpha. Similarly, substitute E is equal to 1 by 7. You will be getting beta. You will be getting beta. So alpha, beta have been computed for this problem. Similarly, we work out one more problem also. The velocity distribution in a wide river is found to vary 1 meter per second at the bottom to 2.5 meters per second at the surface, basing on this expression, according to this expression. Only thing is, small u and capital U are used instead of using small v and capital V. That is only the difference in this problem. Why I have taken up this problem with a different notation is, you may be referring several textbooks. You should not get confused using u at some place and using v at some other textbook. Don't get confused. So that's why I have used here small u, the local velocity, instead of small v. So into 1 plus 1.5 into y by h whole to the power half. In which h is the total depth of flow. In the previous problem, y0 is the total depth of flow. Here h is the total depth of flow. And v is the velocity at any distance above the bottom. And you need to find the values of alpha and beta. Same procedure you need to follow. Alpha is equal to 1 by a integral small u by capital U whole cube into d. Have you noticed what is the change that you have kept here? Instead of keeping small v by capital V whole cube, I use small u by capital U whole cube into d. So small u cube divided by capital U cube into d, where capital U is the average velocity, mean velocity, and small u is the local velocity or velocity distribution given by this equation. So you need to take 1 meter by unit width, 1 meter width of the channel, then the cross section area 1 into 2.5, and the average velocity will be integral of u into dA. Integral of u into dA is the discharge, and dA is the the vectored area of the elementary strip. Per unit width, it is 1 into dy. It is 1 into dy. Substituting that, 1 into h into u based on the average velocity would be equal to integral of 1 plus 1.5 into y by h whole to the power half into dy based on the actual velocity distribution. So equating both, you are getting the value of the average velocity or mean velocity to be equal to 2 meters per second. Alpha is given by the expression same thing, 1 by a integral of small u by capital U whole cube into dA. So make use of same thing. So alpha is equal to 1 by a vector area, unit width into depth of flow h. So 1 into h into integral of small u by capital U whole cube. Capital U is how much? 2. So this 2 cube has been taken out of the integral because this is constant. So this is 2 cube here. Integral of small u whole cube into dA. Small u whole cube into dA. What is this small u? Small u is the velocity distribution which is given by this 1 plus 1.5 into y by h whole to the power half whole cube into dA is the elementary area or area of the differential strip that you have considered, unit width 1 and the depth of flow y. So 1 into dy is the area. If you solve this and substitute the limits, you will be getting the value of alpha. It's simple mathematics. So what is given here is integral of something like a plus b whole cube. A plus b whole cube. So expand that first and try to proceed. A cube plus b cube plus 3ab into a plus b. So accordingly, you will be getting 3ab square and 3ab square, 3a square b and 3ab square. And applying the limits here, you will be getting the value of alpha. Similarly, for beta also, 1 by a integral small u by capital U whole square into dA. No other change. Instead of cube, you have square. But all the remaining procedure is same. 1 by a is 1 into h, integral of 1 plus 1.5 into square root of y by h divided by capital U, the mean velocity 2, you can take out of the differential, into, you will be getting integral of 1 plus 1.5 into y by h whole to the power half whole square. Something like a plus b whole square. Expand that, a square plus b square plus 2ab, and then apply the limits for this, you will be getting the value of beta. So we have calculated the kinetic energy correction factor. You have calculated the momentum correction factor alpha and beta.